We have had around 4 or 5 classes just to begin with, right? The recordings of the first 3 sessions are available over YouTube in my channel. Uh, the link I believe I had shared with Saurav and I forgot, yeah, Saurav and Rohit. So, on the other hand, Prakash, Priya, and Kumar, the three of you are aware of the link, right? So the three recordings are up there in the YouTube, are there up there in YouTube on my channel, and you can directly go to the channel, subscribe, and you can just have a look into it, or you can even directly look without a subscription as well. So, having said that, the next part that we would be talking about is the areas that we have completed. So, what we have done is we have just covered the very basic part of descriptive analytics. We have discussed the very basics of mean, median, mode, measures of central tendency, the measures of dispersion, and so on. And from there, what we have done is we started discussing about the basic concepts of probability in the last class, right? And we have brought in the basic concept. Within probability, we have discussed the very basics of what is meant by probability. How do you calculate probability? What is the classical definition of probability? What is axiomatic definition? And the different aspects related to probability, like probability mass function, probability density function, and so on. So these are the basic things with which we have started our discussions, right? And today we would be talking about, we'll continue with our discussion on probability theory, and I'll just quickly recap the basic concepts of probability distribution, probability. So we'll just talk about the basic concepts of, uh, you know, like how many. So what we'll do is we'll just talk about the basic concepts of probability, mass function, density function, which we had done and which is important for us to take up today's discussion, right? So this is what we had done up to the last class, and from there we would start with the next part. So these are the three recordings, guys, which has been shared over my YouTube channel, and I'll upload the remaining two recordings after we are done with the two classes of this particular week, right? So that is it. I'll just share the link so that the two new people can join over the YouTube link as well. So, however, all these recordings would be going up on the Google Drive as well. It's just that I have been in transition over the last week, so I could not manage to put all your recordings up. So, however, once I'm done, I'll upload them. But till then, you can actually easily just access my channel through this, and you can have a look into the recordings. So, for more complicated, for the more the more core recordings on risk modeling, so they would not be shared out. So I've just shared out a couple of them over here initially. Okay. So having said that, let's just start our discussions for the day. So we have been talking about the concepts of probability theory and probability distribution, right? And while talking about probability theory, we have discussed what probability is, what is classical definition of probability, what is the axiomatic definition of probability, and going forward, we have also discussed what exactly is the you know what are the concept probability mass functions and density function. So today we will be talking about the concepts of we'll extend our discussion to the concepts of distributions today, right? But before that, a quick recap on the concept of probability mass function and probability density function. So we know that probability, or the objective of probability theory, is to help us understand the basic elements of stochasticity, right? So the basic elements of uncertainty involved with the model. And in that respect, what we are trying to do over here is we are trying to you know what we are trying to do over here is we are trying to understand the mathematical framework which helps us in doing this. because this mathematical framework going forward would be really helpful in assessing different sides of credit risk. And today we will be talking about different examples around building these particular distributions. So how does one distribution relate up to another? And how are these distributions applied in credit risk? So before we move on, so just to recap, so we saw that the role of mathematical probability was, or the role of this mathematical version of the probability theory was to ensure that we could overcome the challenges which was created by, or the limitations that were created by the occurrence of discrete outcomes, the occurrence of mutually exclusive outcomes. So, what mathematical probability, or what this framework helped us understand, was that the probability of outcomes or an event or a set of events can be represented by a variable, and that variable was called the random variable. So basically what happened was that, say suppose if I am rolling a die, right? So the sample space we said would take 6 different values. Now those 6 different values can be characterized by a discrete variable, and I can say that let x be a variable which can take 6 discrete values like 1, 2, 3, 4, 5, 6. So instead of saying that on rolling a die there are 6 possible outcomes, what I'm saying is that there is this variable x which can take these 6 values, which can take these 6 values. Now, when I say that x can take these 6 values, right, then what x is called a random variable. Now, why is it called a random variable? It is called a random variable because x is taking, so we know that all the possible outcomes that x might take, but which is that exact outcome which occurs in a particular trial is not known to us. So basically random variable, therefore x is said to be a random variable, right? So a random variable is a variable which takes, or which, about which we know the particular we know the set of all the possible outcomes which are available, but what we do not know is the set of, or what we do not really know is that which is the outcome which will occur in a particular trial. And that is precisely what it means, is that each random variable has a chance associated with each of its outcomes, right? And that is why we call this variable a random variable. So suppose if you think about it in mathematics or wherever, in whichever domain you want to think about it, if you think about it in this way, that that x is a variable, that means what, x can take any values. I define that x is taking a value between a to b. Now that is a sure stuff, I know that ax is taking any values between a and b. But if I ask you now that I tell you to draw a number between a and b, right, what is the probability that you will get the number a by 2, a plus b by 2 in the first draw? Now that is what is uncertain, because there are a lot of numbers which are mingled out, right? And I don't know which is the number I am pulling in. So that is where, whenever there is an occurrence of randomness, right, whenever there is risk associated, that is where probability comes in. And the variable which is used to explain this risk is called the random variable, right? Now, depending on the type of the outcomes, we have seen that the random variables can be of two types. One is a discrete random variable, and the other is a continuous random variable. So there are these two variables which is there. Now, depending on the outcome, say for example, this example of die rolling that I have used over here, I can see that the outcomes are just discrete in nature. So that is where I can say that yes, this is 1, 2, 3, 4, 5, and 6. So that is where the outcome is continuous in nature. So, and this, so now if I am saying that the probability of x equals to x, so x is the variable. So what is the chance that x will take the value 1? What is the chance that x will take the value 2? What is the chance that x will take the value 3? And so on, right? So therefore, what we are trying to do again over here is we are trying to understand, we are trying to assess the riskiness associated with each of the outcomes, right? Or the chances associated with each of the outcomes. Now, yes, in the last class we discussed that this function or this experiments or these outcomes can be written in a mathematical form. And when I'm writing those mathematical equations, so when I'm writing a random experiment in a mathematical format, right? Depending on whether the outcome is continuous or discrete, we call them probability density functions or probability mass functions. So now, I mean, this the way I frame the stuff might seem complicated, but that is not complicated at all. So let us see how or what is it that I'm talking about, right? Let's say, let's take a very realistic example and let's try to frame a mathematical function which can express a probability. Now, you know that a very famous or a very prevalent model in risk is the probability of default model, right? Or the probability or an origination model where a bank is trying to assess whether a borrower is a good borrower or a bad borrower. So over here, what happens is, so let's think about it in this way, that at origination, there is a borrower who comes up asking for a loan from the bank, right? So for the bank, the dependent variable of the business problem would be y equals to 1 if the borrower defaults, if, or let's say if the borrower is good. So if the borrower is good. Y equal to 0. So over here, so y equals to 1 if the borrower is a good borrower is equal to 0 otherwise, right? Now, from here, what we are needed to do is that, so what would the bank do? The objective of the bank is to predict the probability that the borrower is a good or bad borrower. So I'll just describe this case once again and then we'll move on. So the idea over here is that there is a borrower who is coming up to take a loan, right? So he's applying for a loan. Now the question that the bank is faced with is that should I give him the loan or should I not? So should this borrower be given the loan or should this applicant should be given the loan or should this applicant not be given the loan? So that is what the problem that the bank faces at origination. So the problem of the bank over here is to estimate the probability of y equals to 1. So this y over here can take two values. Y equals to 1 if good, equal to 0 otherwise. Let's just hold on a second. Okay, am I audible, guys? Hello. Yes. Thank you. Okay, so as I was saying, that so as I was saying, so for this bank, who is just trying to acquire a good borrower or a bad borrower, we're just trying to understand that. So all he can do is he can try and estimate the probability of the borrower being good or bad, right? Now, for doing this, how will the bank go about doing this? So what the bank will do is bank will look up a set of factors, like, so the bank will look upon a set of factors. Say you look upon the factors like income of the borrower, income of the borrower, right? The employment status of the borrower, the employment status of the borrower, and so on. So there are a lot of these different kinds of variables which will come. Now, say I can say that okay, when the income of a borrower goes up by so and so percentage, the probability of y equals to 1 goes up by so and so percentage, right? Now looking into all these, what I can do is I can actually frame a functional form, right, which will relate the movements in this income and employment status and other such variables to the probability of a borrower being good or bad, right? So once this is done, then the next part is, so basically what I need to do is I need to create a functional form. So let us say I write a functional form like this. Now why I am writing this functional form is something I'll come down later. So when we talk about the more advanced form of modeling techniques, that is where we'll come down to this. So say I have this probability of y equals to 1 is, say I write it as 1 divided by 1 plus e to the power of beta 1 x1 plus beta 2 x2. Say I write it like this, right? So whenever I get a value for x1 and I get a value for x2, I will be able to compute a probability of y equals to 1, right? So let's think about this case that the first borrower comes out to me, right? So this first borrower is a trial that is happening in the lending process, because when the borrower is coming in and I'm giving him the loan, there is always a chance that this borrower might turn out to be good or he may turn out to be bad. Similarly, on the other hand, when it happens is a beta 1, so basically the second person comes in, I try to give him the product, and that is where I get to see whether he is a good borrower or he is a bad borrower. So it is this way that a mathematical framework can actually be created to estimate or calculate the probabilities. Now, calculating this probability and this equation itself is the whole modeling technique that we talk about. So, I am just using the example over here to demonstrate the concept of this probability mass function or probability density function, as we are as we may think about it. But since over here this x1 and x2 can be continuous variables, therefore this is a typical example that I have created of a probability density function. So this is the PDF of a probability of default model. So by using this mathematical framework, what I can do is I can actually represent the probabilities of a borrower of being a good or being a bad borrower, right? So is this part clear, this example, and how is it that I'm relating it to the concepts of probability, or I mean to the probability mass function and density function? So how probability can be used, or how can a mathematical equation on probability be constructed using I mean using such a case, right? So, and where is it applicable in the risk domain? So is this part clear? If you have any queries, feel free to ask. Okay, so if there are no questions, then I'll move forward. Okay, so PDF is for continuous variables, and PMF or probability mass function is for uh, you know PMF is for discrete variables with discrete outcomes. However, over here you know the variable is not important. What is important is the outcome. So whether the outcome is discrete or continuous. So over here, when I talk about employment status or such categorical variables, so when we go into the model development, we will see that there is a topic, there is a concept called weight of evidence, right? A weight of evidence kind of a transformation, which will help us convert the categorical variables into continuous variables, and thereby will help us in get generating probability density functions. So, however, remember that when I'm talking about probability mass function or probability density function, what I'm essentially talking about is a set of continuous or discrete outcomes. Now, this is what we have observed at an account level. So, basically, when a borrower comes in, I want to predict what is the probability that this borrower is a good borrower or a bad borrower. So, the outcome is continuous in nature because probability is a continuous variable. Now, the outcomes that are, or I mean, so the probability is being estimated basis the input variables, right? So if x1 takes this value, x2 takes this value, x3 takes this value, then how does my probability figure look like? So over here, we need to ensure that x1 and x2 and x3 they are all being entered as continuous values, and that can be done. So even if there are categorical variables, there are techniques of converting them into continuous values using certain ordinal transformation. So we will talk about that part as well, right? Okay. Now, having said that, the next thing that we'll talk about is okay. Anirudh, Prakash, am I audible, guys? Can you guys hear me? Okay. Okay. Now, let us look into another example. The example of which is an extension of this, right? Now, see what I'm in this first example, what I've stated is that there is a borrower who is coming up and asking for a loan, right? And I'm estimating the probability. So obviously the inputs that are going in are so created that they are continuous inputs, and from there we are generating the we are trying to estimate the probability. Therefore, since the since I'm trying to generate the probability under different continuous inputs, therefore this is a probability density function. Or since the outcomes of the variables which are used to estimate this probability, since those are continuous, we are saying that this is a PDF. Now let us generalize this case. I mean, let us just think about this case in a different manner. Now suppose that the bank who is designing this lending process, right? So who has designed this scorecard and has practiced this or has this lending practice? Now suppose that bank has, say, there are, say, 1,000 people on the books of the bank, right? And for each of the person, right now, what the bank wants to know is that what are the probability that given the lending strategy, given the scorecard and everything, given everything, what is the probability that there would be, say, around 10% defaults, or what are the probability of getting 100 defaults out of 1,000 loans, or if there are 10,000 loans which are being given out, what is the probability that they would get around 10 defaults, 100 defaults, 20 defaults, like this. So now if you think about it, the the event for which the probability is now being calculated has totally changed. Now the bank wants to know that given that it has an average probability of good borrowers and it has an average probability of bad borrowers, right, based on its historical, based on its historical experiences. Now, what is the probability of getting some specified number of good or bad borrowers? So we can think about it this way. So a bank has been practicing a lending product, right? A lending policy. Now the bank introduces a new policy. Now when the bank introduces a new policy and is willing to implement it, before doing it, they'll obviously do a pilot survey. Now, out of doing that pilot survey, they see that the overall probability of a borrower to be a good borrower is something, and the overall probability of being a bad borrower is something at a portfolio level. Now the bank wants to, in that portfolio, the bank is bringing about a new product in that same portfolio. Say in a credit card, they are trying to bring in a new type of a credit card. So what they now want to know is that if they start off by distributing, say, 10,000 credit cards, what is the probability that there would be, say, 100 defaults or less than 100 defaults, right? So if after while they give out, say, 1,000 credit card, if is a 90% success rate, or if 90% of the good borrowers are good borrowers, then the bank is willing to go ahead with the strategy at a larger level. So now the problem of the bank changes to find out the number of defaults that is probable, or what is that default which is most likely to occur. And that is where the outcome becomes a discrete outcome. So now the bank is no more estimating a probability. Now what the bank has is that on a historical average, on a historical performance, it has seen that on an average, the portfolio has, say, around 80% good borrowers and 20% bad. So they say that, okay, the overall the average bad rate in the portfolio is 20%, 10%, say, and 90% is the good rate. Now, if in this portfolio, if I introduce a new product, what exactly are the chances of getting some number of defaults? Say I want to know what is the probability of getting 99 defaults if 1,000 credit cards are initially distributed to people who satisfy certain criteria. So now when I want to find out the probability of some number of outcomes, that is where the dependent variable or the outcome variable becomes discrete in nature. And when I want to express this, when I want to identify this as a particular, in a mathematical function, as a mathematical framework, what I end up getting is the concept of a probability mass function. And when I write the mathematical framework in a very generalized form, what I get is, again, what I would get is the what I would get is called the probability distribution functions. So is the difference between these two examples clear? One that I wrote over here and the one that I just discussed now. So are you clear about when I say that the outcome is continuous versus when I say that the outcomes are discrete? So are you able to identify this difference through the two examples that I had shared? Great. So we'll just try to see this case that I described over here of the bank trying to do this exercise. How this function can be formulated and what exactly is this function? What exactly is this distribution called? What are the properties of such functions and so on? Right? Just guys give me 2 minutes time. I'll just finish my lunch and I'll be back. Just give me 2 minutes. Okay, so let's just construct this example that we were talking about. So basically, let's think about it this way. So basically, there is this bank who wants to run a pilot survey of introducing a new product on 10,000 new on 10,000 applicants. So it is actually trying to give the new product to 10,000 borrowers. So now think about it from the bank's perspective. Now the bank is giving this to 10,000 people. Now when the bank is doing this, obviously the bank is increasing its exposure to risk from these 10,000 borrowers. So now when the bank is actually giving this, the bank wants to know that what is the probability of getting defaults of say less than equal to 200. So what is the probability of getting default of x less than equal to 200? So x is default. So basically if default happens, then I will say that success has occurred, else I will say that failure has occurred. Right. So now observe this outcome. Now the outcome is the number of defaults. One default, two default, three default, four default, five defaults, like this. So this shows basically the number of defaults that actually the bank is expecting. So what is exactly the probability of x being less than equal to 200? So what is the probability that I'll get defaults less than equal to 200? So that is what I'm trying to estimate. Now, when the bank is trying to do this analysis, the bank must needs to know two things. That on an average in that portfolio, what is the percentage, what is the rate of the good rate and what is the bad rate? So how do I define the bad rate over here? So bad rate over here is nothing but the total number of bad borrowers divided by the total number of borrowers. The idea is total number of bad borrowers bad borrowers divided by the total number of borrowers. So this will give me the chances that a borrower on at the portfolio level can be bad. Right? Now this concept of bad rate is going to play a very critical role in risk analytics even going forward. Right? So basically when we are developing PD models, LGD models or scorecards, the concept of this bad rate is going to be really very important going forward. So be very clear about this concept of bad rate, right? So so the bad rate will give me in this case the success, right? It's the success, and one minus the bad rate will be your good rate. So one minus the bad rate will be your good rate. So let me represent bad rate by the probability or the probability of success, and let we denote good by the probability of value of q, right? So what I have is the probability of good and probability of bad. So now over here, what I want to actually do is I want to know that what is the probability of getting less than equal to 200 defaults. So what will I do? So what I want to know is that what is the probability of getting one default plus the probability of getting two defaults. Like this, the probability of getting 200 defaults. So the total sum of this will give me the probability of getting default which is less than equal to 200. Or if I say I'll just sum up the probability of x equal to x from 0 to 200. So this is what the entire idea is. Now the question that comes out is that how will I calculate or how will I express this probability of default? So how will I calculate this x equal to 2, or how will I calculate this x equal to 1, or how will I calculate this x equal to 200? How will I do that? So that is where the next part comes in. So I need to create a mathematical representation for this. So let's think about it. How can we do this? So basically, what I want to find out at one given time is that what is the probability of getting x number of defaults. That is, what is the probability that x will take up a value is equal to a specified value of x, right? Now, when this happens, when this happens, the next part that we talk about is that how will I calculate this? What is the probability of getting, say, two defaults in a trial of 10,000 borrowers? So for doing this, I need to go back to the basics of probability theory. I need to understand that how is this probability created. So this probability is created as the number of favorable events divided by the total number of possible events. But over here, I cannot essentially do that. The reason is that this I'm saying that what is the probability of getting two defaults? But these two defaults might occur in many ways, multiple ways in this 1,000 loans, right? So if I'm doing 1,000 lendings, it might be that the first two loans default, the remaining 998 loans, 9,998 loans do not default. It might be that the first 9,998 loans do not default, the last two defaults. Or it might be that the first loan defaults and the last loan defaults, but in between none of the loans default. So this can occur in different selections, right? And I cannot capture out all the selections. So I need to go about it in a more mathematical, or I need to go about it in a more technical manner, right? Now, if I'm going about it in a more technical manner, how does it work? So what I say is that, okay, let me take an arbitrary situation that when I give 1,000 loans, the first two loans default. So default, default, and then not default, then no, not default. That is, none of the loans turn out to be default up from the third right up to the last observation. Now observe that the loans that have been given were given independently of each other. Therefore, each of the outcomes are independent of each other. So from here, what you can see is that that the success in this experiment or in these trials or among these trials have happened only in the first two trials. The remaining 9,998 trials have turned out to be a simple failure. So this is one possible case. So that means over here, P has realized, that is the probability of success. Over here, P has realized, but then for all the other trials, Q has realized. That means over here, what we get to see is there is P square into Q to the power of 9,998. So that is, success has occurred twice and failure has occurred the remaining 9,998 times. Hence, and since all the events are independent of each other, we know that if there are two independent events, then the probability of A intersection B is probability A into probability B, given that if the events are independent of each other. Coming from that perspective, we can say that this P's the probability of success over here is P square into Q to the power of 998. But again, observe that there this thing has happened in one particular pattern, and to this there might be multiple patterns, right? So there can be multiple arrangements, multiple selections that can be made out of this. So one P can occur, one success occurs in the beginning, the last success occurs at the end, in between all our failures, or one success occurs in the second success occurs in the 10th position, then all the remaining are failures, and this can happen in any possible way. Therefore, we need to take into account all the possible selections. So this is the probability for one selections. Therefore, if I need to select two successes from a trial of 10,000, how will I do that? So to do that, I will use the combination function. That is 10,000 C2 into probability into P2 into Q to the power of 9999. So this shows that the probability of obtaining some number of success, right, or obtaining a defined number of successes out of a defined number of trials, where each trial has a given probability of success and a given probability of failure, can be calculated in this manner. So this is known as the binomial distribution. This is the probability, the binomial probability mass function. So and this is precisely an extension of the other function, so which is the Bernoulli's distribution, the Bernoulli's function. So Bernoullian distribution is defined for one single trial, right? So any trial which has a probability of success and has a probability of failure is called uh, a Bernoullian trial. So whenever I am taking a trial and there is a chance of a success and there is a chance of a failure, then that is called a Bernoullian trial. So whether it be coin tossing or giving out a credit or rolling a die or any such events where each of the trials either have a success or a failure and nothing in between, then those trials of then the trials are known as the Bernoullian trials. So if I am actually investing in the stock market, so I have two outcomes. I can get a success and I can get a failure, right? So I can make a profit or I can make a loss. So there is a probability of success, there is a probability of failure. Therefore, that investment becomes a Bernoullian trial. And when the Bernoullian trial occurs, or this Bernoullian kind of an experiment is executed for some n number of trials, that is where I end up with the binomial distribution. So this part of the binomial BMF, so this part is called the binomial distribution, right? So over here you see that the outcome of for which I'm computing the probability has become continuous. And in this way, so we what we have seen now is is an extension of the theoretical section that we did in the last class. So we had discussed about probability, mass function, probability density function, mathematically and mostly statistically. So in today's discussion, what we are doing is we are exploring the risk example, an example on risk where these concepts come in handy. There. Clear? Is this example clear? Any doubts? Any confusions? Especially Saurav and Rohit. Okay, great. Okay, so I'm just coming on this part of the discourse once for on everything. See, what happens is I'm saying that let me take the case that I'm giving a loan, right? So now I know that there can be a success, there can be a failure. Now over here, what we have is, say, I'm giving a loan, right? I give the first loan. Now the first loan may turn out to be good or it may turn out to be bad, right? So to each trial, there is always a probability of success and a probability of failure. So suppose I give the loan, the first loan, and the first borrower is the defaulter. So over here, the success is, for me, success is my default. So basically, default is the event. So I want to model the chances that how many defaults will be there. So that is my subject. So that is my target. So what I say is okay. In the first case, what happens is P realizes. That is the default actually happens. Now, in the second event, I also try and I see that yes, again the loan defaults. So I now again have a success over here. Now, observe that trial 1 and trial 2 were independent of each other. Now, given that they were independent of each other, therefore, the borrower would not, therefore, the probability that the fact that the first person turned out to be a defaulter would not necessarily imply that the second person will also turn out to be a defaulter, right? So over here, so if A and B, both of them, they appear to be defaulting, then they both default. So trial one and trial two both default. then they are independent of each other, right? Therefore, second problem, even in the second case, success realizes. Now comes the third case. In the third case, in the third trial, what I see is that I give the loan, and this borrower, he actually turned out to be a good borrower. So over here, that means which is the fact that realizes. Now, when the loan was given, he both had the chance of being a good borrower as well as a bad borrower, and he actually turned out to be a good borrower. That is, he did not turn out to be a default. Therefore, now the probability of success, and the probability of failure realized. Now, the fact that in the third trial a failure has realized does not bear its relevance to the fact that for the first two trials, success was realized. So, the fact that failure is realized in the third trial is independent of the fact that failure success is realized in the first two trials, right? Now, similarly, now I wanted to know that what is the chance of getting two successes, right? So, if the first two have come out as success, now that means what the remaining 998 trials will go as failure. That is, two defaults have realized, the others are non-defaulters. So that is where this cube up to 10,000. So basically for the first two case, I have what is p to the power of q square. P to the power of square and q to the power of 9,990. So what does this part actually try to tell us? So over here what I have is, so this figure or this, this part, what it shows me is that exactly two successes have occurred in 10,000 trials. So thus it's not just that two successes have occurred, but it is just that two successes have occurred in 10,000 trials. Therefore, the chances are so basically, if exactly two successes are occurring in a 10,000 trials, then what it essentially means is that I'm computing the following probability. Probability default equals to 2, and non-default equals 3. So what is the probability that there are two defaults and there are 9,998 non-defaults. So there are two defaults and there are 9,998 non-defaults. Clear? Anirudh? Okay. So now the question is, so coming to the next question. But if the question is what's the probability of less than 2? So probability of less than 2 is what? Probability of x equal to 0 plus probability x equal to 1. So I'll compute that what is the probability of getting 0 trials, like 0 successes, plus what is the probability of getting one success. Because since the outcomes are discrete in nature, therefore I can obtain that similar just by adding the values. So basically probability of x less than 2 is nothing but the probability of x equal to 0 plus the probability of x equal to 1. So when I'm computing the probability x equal to 0, what it means is the probability of getting 0 successes and 1000 failures. When I'm computing the probability of 1 of x equal to 1, it is nothing but probability of getting 1 success and 9999 failures. Clear? Again, if you see it in another way, Anirudh, it shows that, so if I want to compute the probability that the default is less than 2, so what it means is that the default is less than 2 and non-default is greater than 9999. So basically over here what I'm doing is probability of x equal to 0 and failure 9999 plus probability x equal to 1, sorry, probability x equal to 0 and failure equal to 1000 plus probability x equal to 1 and 9999 failure. So that is what I'm computing. When I add the two up, I'll get probability of default to happen less than 2. Yes, great. So this is precisely what the binomial distribution is. Now, this binomial distribution, or binomial probability distribution, will be playing a very critical role throughout this domain of credit risk modeling, right? Because based on this, so most of the, when we are going into the modeling side of things, when we are trying to estimate the parameters, we are doing it. So we are doing it because we want to frame an idea. So basically, uh, whenever we are going into do this estimation exercises, so all the population, for example, they follow this binomial distribution, and the fact that they follow the binomial distribution stems from the very fact that they start with, or so it stems from the very fact that they are, I mean, that the business variable is defined in this manner. So the question that comes out over here is that how would a binomial distribution look like? And just before I move on with that, a quick recap on the fact that a binomial distribution is nothing but it is a extended generalization of your, so this is an extended generalization of your like what's your role? The extended generalization of the Bernoulli distribution. So what we'll do is we'll start off talking with, I'll just start by framing up the mathematical representation of the binomial distribution. So a binomial distribution looks like this. So it is like this in Cx. So this is the mathematical symbol for combinations. P to the power of x and q to the power of n. Now, the question that comes out is that whenever a mathematical, whenever I'm doing this mathematical formulation, I need to ensure that this is done under a typical assumption, right? So this will be done under a kind of a typical assumption. And what is that assumption over here? So those assumptions must be there, and it is those assumptions which make it the probability mass function, right? So basically, I can only write this even only the following conditions are satisfied. That is, if x starts from 0, and p plus q is equal to 1. Now these two are really very important. Number one, it shows that the outcomes has to be discrete and finite. This is discrete plus finite. And the p plus q is equal to 1. That is, every outcome has either a probability of success or a probability of failure. So it cannot be that I toss a coin and it stands in between, neither heads nor tails. So either heads come up or tails come up. Also, cannot be that it is totally biased. So therefore, that is the reason that this p plus q must be equal to 1, right? And this ensures that the trials are Bernoulli in nature. So a Bernoullian trial is a trial where you have some n number of trials, and with each of the trials, you know, what you get to see is that uh, so this ensures the last condition ensures that the trials are Bernoullian in nature, right? So therefore, if if there's a probability head or a probability of tail which comes up, so basically, if I toss a coin, it must have two outcomes, either a success or a failure. A trial like this is called a Bernoullian trial. And if any one of these assumptions are not satisfied, then it becomes an impossible game. Like over here, I cannot compute the probability of getting infinite successes or infinite failures. I can only compute the successes if the number of trials are discrete and finite. But observe that with this outcome, or with this mathematical framework, you can compute cases where outcomes are not totally mutually exclusive, where both can coexist. So it was not possible using the classical probability definition. So over here you are actually calculating the probability that there are two defaults and some n number of 9998 non defaults. So now this kind of a probability calculation was not possible with the classical definitions, right? Clear up to this part. Great. So what we did today was, first we linked up the Bernoullian distribution which we had done in the last class to its extended general version, the binomial distribution. The second that we have done over here is that we have explored a good couple of examples to relate the concept, where we can relate the concept of probability to risk, right? So the idea is just to understand that whatever we are doing is not just a mere theoretical concept, but it also has a relevance to the risk analytics that we are working around. Okay. Okay. So Anirudh has a question that, so is this is axiomatic? No, Anirudh, this is not axiomatic because I am not putting in any axioms over there. Now axioms are something which cannot be challenged, so they form the premise of the discussion. Over here, I am mathematically or functionally deriving the frame which will give me the probability corresponding to the outcome. So this representation that we have been talking about and we are focusing around is the it's the mathematical probability framework. So it's a framework of the mathematical probability, right? So the idea over here is that what we are trying to do is we are trying to extract the results out mathematically. Now over here you can see that when you put in a value of x, you will get a value of the probability. So what you can essentially do from this framework is you can ideally create out a schedule where by putting in the value of x, you can compute or you can obtain the value of probability x equal to x. Okay. So okay. So to your question on Anirudh, so Anirudh has a question that, but when we are talking about axiomatic approach, so axiomatic approach is the outcome. I mean, it's when outcome is discrete and finite, but not mutually exclusive and equally likely. Correct, Anirudh. But over there, you would see that those derivations or all these examples that we had given was based on certain axioms. So, so we had used those set theoretic axioms from there, and we had used them. But over there, using the axiomatic approach, we could not interpret that of the continuous outcomes. This kind of thing was not explainable. So what we where we moved on to was the mathematical probability framework, where we tried reducing down or we tried deducing those results that we had set in the axiomatic approach in a more mathematical framework. Now, that is where we had defined probability mass function and probability density function, where by putting in the value of x, we were able to generate the probability of values dependent on that. So therefore, when we are talking about mathematical probability, this is a more generalized framework. So all the outcomes that axiomatic approach could deduce are also deducible under the mathematical framework. Also, over and above that, we could also extend it to the more continuous framework, right? Great. Okay, fine. So now, having said this, this probability over here. So now you see that. See, if you put x equal to 0, you can compute a probability x equal to 0 using this particular function, given that the values of n and p are actually provided to us. So x equal to 0 can be computed. So you give x equal to 1, probability of x equal to 1 can be computed. X equal to 2 can be computed and so on. Right. So basically over here you see that you can compute the probability given that this value of n, the number of trials and the probability of success is available to you. Right. Therefore, this n and the p is known as the parameters of the binomial distribution. Known as the parameters of the binomial distribution. So we often say that if the behavior of a variable x has all these characteristics which are required for setting a binomial distribution, we say that x follows a binomial distribution with the parameters n and so x follows a binomial distribution with the parameters n and p. Clear? So n and p are called the, you know, they are called the parameters of the binomial distribution. Now, having said that, let's look up more deeper into this. So the next question that comes out to me is that how does the distribution look? How does it look like? So I have been talking about a binomial distribution, right? So how would this distribution look like? So would it be a symmetric distribution or would it be a skewed distribution? So before you give me the answer or before you initiate your thought process, just let me refresh on the fact that what exactly is distribution, right? What exactly is this uh, concept of a distribution? So basically, the concept of a distribution is where you have an outcome and a relative frequency corresponding to that outcome. Right? So over here on one axis, what you do is you plot. So this is where you plot the outcome x, and over here what you do is you plot the relative frequency corresponding to the, and it's a graph like this. So when you plot the outcome and the frequency, what you get is the relative frequency curve. Now the question that comes out is that For the binomial distribution, so have a look into the binomial distribution, right? So you can see that. Can you tell me by looking by into this function, how do you think? So basically, given the value of x equal to 0, I'll get a probability 0. Given x, I'll get a probability x equal to 1. Given x equal to 2, I'll get a probability x equal to 2, and so on. So how does this one look like? How would the graph of the distribution of the binomial distribution look like? So for this, so is it skewed? Is it like not skewed? Is it symmetric? So how do you think this distribution, this binomial distribution should look like? Okay. So basically, a binomial distribution can be both asymmetric, can be both asymmetric, very skewed, as well as can be symmetric. Can be asymmetric as well as could be symmetric. Right? So how does the point look like? So how would it look like? So it can be both symmetric and asymmetric in nature, right? Now, what I leave you to is to analyze when can this distribution be symmetric and when can this distribution be asymmetric, and what should be the logic behind making a binomial distribution as symmetric versus asymmetric, right? So today I'll stop here, right? And we'll take it up from this point tomorrow. Tomorrow we'll talk about the important, the matrices, or I mean, the important moments of binomial distribution. From there we'll move into the Poisson and then the normal distribution. Right. So tomorrow's class we'll be completing this probability distribution part, right? And in the meantime, what I'll be doing is I will be sending or uploading the other these three recordings to the YouTube channel. So once you finish off with as you are finishing off with one part, I am just uploading it so that everyone can see the topic wise recordings, right? So thank you guys. That's much from my end, and let's meet next week again. Thank you. Thank you guys. Thanks a lot. Bye bye.